plus minus 1. And if you know, because here I don't have some different equations, so looking of the hypergeometric function, so I skip to write all the equations. So basically here it means that that is singularity or the singularity minus 1. If you go for hypergeometric function 0, 1, infinity, if you go for suppose Bessel, and your singularity may also be arise Lagrange singularity may be also arise 0, 0, infinity, whatever like this. So this is most important, and also having very physical significance. So basically, I would like to suggest to our new researchers, those who are interested to work on the differential equations, some all these special functions. This is most important to learn what is the need. So this is first point always put in our mind, that what is the need for doing this work. So this is given. So this were our some little bit some concept of of the special function, and here we give some interesting work of this now. So let us come on the hypergeometric function. So basically, hypergeometric function that is given by this our equation. This is given by 1.1. As you know, this is hypergeometric equation. And in hypergeometric equation, this can be also expanded into form of this equation. Condition is this. So basically, mod of z is like that. So it means here we are using z. That is any complex value, complex number. So complex number. So basically, here we're discussing about this any you can say that is circle or disk, whatever you can take it. This is the convergent condition. Is this the mode of z is less than 1. So less than 1, it may all the point inside the circle. And here this is convergence condition. This is given like this p is less than q, as equal to q. Then okay, this is always this convert absolutely for every finite value of z. And if I put p equal to q plus 1, this is converts when mod of z less than equal to 1. And the series will be divergent about when mod of z is greater than 1. Interesting concept is this, why we are putting the mod of z less than 1, greater than 1. And so here also I would like to give the concept of when we using the convergent and the divergent. It means divergence simple, this means that is not existence. Not existence, and the conversion that is the existence of the function or polynomial whatever. So basically, when we are having polynomial, there is no need for discussing whether it is conversion and divergent. Polynomial that is always conversion. That's no problem for that now here. So this is about the first given some concept of the little bit hypergeometric function that is given by the Gauss. And if you see Gauss work a lot of work Gauss done in the in physics. So it means you can think in during that period there is no nobody differentiated this is the physics or this is mathematics and this is whatever some other field. But now this is new names are coming, and actually created so many subjects, so many topics, so many titles, whatever like this. So here after this now. And this is called this right type hypergeometric function. This is 1.3. A problem here, so big difference like this. Here we will discuss about this the concept that is given in the form of the gamma function. And but here in the case of our this one in the hypergeometric function, this is totally given in the form a going to k, b going to k, and c going to k. So it means they're not worried about the fractional value and the real value. So it means here we can take a going to k. It may a is equal to 1, 2, 3, 4, 5, 6, 7, so on. Like ultimately you will get all the values without any fraction. But here in the case of this when they put in this right type hypergeometric function, so it means there you will get this over this parameter into the gamma function, and here this is the condition for this. In this condition, it means that is also due to concept of some conversion. But basically, here we see the mu1, mu2, b2, b3, bq, and here in your numerator b1, b2, b3, b4, bq, whatever like. So basically, it means y. It means your denominator. If it is denominator is this, the denominator plus the ultimately, it means if I divide the denominator with this mu with b, ultimately you will get something by adding. So it means basically mu means that is the greater than this. Greater than this. It will have to making the series converted. If I adding this one, then that would be greater than 0. And this is now given by this. So yeah. So and this can be one case to convert this into form of the hypergeometric function. And so this can be also. So if you remove this gamma function and putting this in the form of the going to form, and we can say that is in the form of the cosine symbol. So then also can be written in the form of the hypergeometric function. Now here the function 2r1. So here we are using this 2 parameter, this omega and mu, that is given by this. Here omega mu, and finally this gamma c and the gamma a gamma b. Ultimately it's a gamma a plus n divided by gamma a. What is the meaning of this? A1 to n. Okay, if we say like this, suppose, so it means basically here we put one thing. B is there, B is there, C is there, and C is there. Ultimately it's 1. But basically this one is totally in the form of the a going to n, and these are into gamma function. And also because this omega upon mu, omega upon mu is this, omega upon mu is this, it will also give some value that is called omega upon this mu, that this is greater than 0. And this has been written into this form that is given by the Burchenko in 2001. So basically this type of work is up to 1935. And I think given this 1935. And after this Burchenko started, between this one or two people were there based on some just like function. And Burchenko used this one, and after Burchenko and this Kriyakova also worked on this type some hypergeometric function. But here you see very wonderful work done by Burchenko. He is from Ukraine, and Virginia Kriyakova from Bulgaria. And she used many hypergeometric functions by using this technique and putting in the form of some fractional, some fraction. And this is this now. So this basically here we will discuss some hypergeometric function of this, and this put it in the form of this in a 2R1 series. This is also in a 2R1 series with the tau is here. So this is parameter, this is parameter, this is parameter, and your z is here. So z is your simple your variable, and you can say this is your argument. And here, first important theorem, this is we can put in the form. This is called recurrence relation. So recurrence relation means what is the need of recurrence relation? So many very beautiful property in the spatial function, that is the different relation. If you go in the gamma function, so you know gamma n plus 1, gamma n plus 1 is equal to n gamma n. So one can raise the issue when all the property are having, but what is the use of this type of resistance? Basically, generally, at the definition of the gamma function, we used to say this gamma function, gamma n, suppose there, so gamma n equal that much greater than 0. But here, when we use the recurrent relation, so we can also find out the value of the gamma minus half. So it means this gamma minus half is there, it means gamma minus half exists. So basically, here the interesting result. Concept, it means when we are having this positive integer, we can say that some natural number, then the gamma function is existing. If I put in the form of some rational number, or we could put in some fraction, and that also give very interesting. But if I say the gamma minus 1, gamma minus 2, gamma minus 3, gamma minus 4, but during that period, the gamma function does not exist. If I say gamma half, okay, no problem, gamma minus 1 upon 4, some other like it is basically simple. We can use the concept of flow differentiation. For example, gamma n plus 1 is equal to n gamma n. Now, so it means now if n is equal to minus half, so you will get the minus half plus 1 is equal to this is the n, and minus half into gamma minus half. Ultimately, your 1% positive value convert into the negative side of value, and you can have to find out the value of gamma minus half. And a problem is now here, but gamma does not exist for negative value. So what is the provision? Under which provision the gamma minus half exists? So it means basically if you see the gamma minus half I it means so basically if you go for the control gamma minus half gamma minus it exists only for due to this recurrent relation. Due to the recurrent relation. Now basically you can define what is the recurrent relation means V plus occurrence. V plus occurrence, which is V means again and occurrence means this is occur over. This is that is the occurring one by one. Again, you will get the uh, you will get this is appearance simple. We can say that is the V appearance. So ultimately, gamma n plus one. A problem with gamma is not defined for the minus value, but here gamma half is existing. It means you but all the term have originated from main function. Main function is the gamma n plus 1. So gamma n plus 1 it means the gamma n plus 1 will always positive. Gamma n plus 1 is always positive. Whatever the our this is you can say this is our right hand side terms. So we are always bothered about it, whether positive, negative, whatever like it. But it means but about the left hand side value, this is gamma n plus 1. So gamma n plus 1 must always be positive. So this is the basic reason. So due to this, reason, this type determination is the most important. And also we can use this type determination in orthogonal polynomial also. In orthogonality, if we are having the recurrent relations and the three-term recurrent relation, there is no need for finding the uh, orthogonality. If the three-term recurrent relation means n plus 1, n minus 1, whatever, like this, or n plus 1, n plus 2, whatever. It means this type of relation is occur. So it means if we are having such a relation, then we claim, okay, this is the your orthogonal polynomial. And about the recurrent relation, it means when we are able to do it, it means this contain also some derivative function. Because derivative function, if you go for finding the derivation, that is also most having the application for having the recurrent relation. That is also not and you can also construct a difference equation that is not in discrete mathematics. Those who are teaching difference mathematics, they can understand this is the difference equation. These are some difference equation, and this is basically in our field. This is known as the generating function or the recurrent relation obtained by using the concept of the generating function. So now, so anyway, so this theorem. So basically, the theorem. I'm not going to prove this theorem. Simply this is all published work. So this is 2.2.1 and 2.2. So this is the form of this. So one can easily obtained by calculation is very tough, not so easy. So we can also convert this into form of 2.2.3 as a special case. And the special case is there. So it means A, B, C, D, and the other C minus 1 and whatever it means. So this can be also converted in the form of tau is this, if tau is equal to, if I put 1, tau is equal to 1, then we will get this one. So this can be really converted into this form. And second, now here, this theorem 2.2. In theorem 2.2, we can use this as the ABC and delta. They belong complex, the complex value, and the condition imposed here. This is the greater than 0 and tau belongs to n. So this can also be put in the form of this. So it means here this result gives in the form of this 2.2.4. And next now the next one is that is given in the form of this ABC, and this is delta. Delta is here, and this is your lambda, and it belongs to C. That is complex value, complex number. And upon the condition of B, this is the real value of alpha, beta, sorry, A, B, C, and delta greater than 0. And this is your capital N. This is your natural number. So finally, this can also be reduced into this form. Ultimately, this relation. If we see so x minus x raised to delta minus 1, so this increased by this now C. So it means this becomes your C. So this becomes C. So C is here. C minus 1 is now. This is the 2.5. This is 1. And third one is also by using this. So here we take the T minus C minus 1. C minus 1. This can be also put into this form. This is this type of example if you see in in gamma function. So gamma function. So we can also, so but in the case of the gamma function, this is now here you will get infinity. Here you will get infinity, and this put in the form of e raised to power minus t, e raised to power minus tau, whatever you want to consider. This is up to you. This will be the t. So here we are integrating with respect to t. So that must be e raised to power minus t. And now this is a very special case, well-known case. So this can also be reduced into this form, 2.2.7. Next, now this is your differential property. If we go for differentiate this m at time, so that gives equation 2.2.8. Now, to representing this right-type hypergeometric function in terms of the PFQ form, PFQ form. So here we can write 2f. This is given like this. Now, a, b, c, tau is this, and q plus 1 f is this. Ultimately here is b upon q, and this is b plus c plus like this. So it is now that to Q form, and this is the most important. This is Millen-Barnes integral representation. This is very wonderful if you see for an special function and a polynomial. And if you're this is introducing a Millen transform. So ultimately, there's given concepts of this is Millen transform. So ultimately, so here that gives by Millen gives this in the form of some Millen and Barnes. Gives this integration of the gamma function. Basically, that is integration of the gamma function. This is not good. So integration of gamma of that means this is called this is the Millen-Barnes integral representation. So it means this equation this can also put in the form of this Millen-Barnes integral. This is the gamma s, gamma a minus s, gamma b minus tau s divided by gamma c minus tau s minus z raised to power minus s ds. So and here we contour it. This is basically you must aware about the contour integration. So contour integration starting from this minus this, so minus this and ending this starting from this to this. I think this is some block some this one. And here giving into this form, and you can also plot the graph for this and also go for some different type of interpretation of this as per your needed and your requirement. And here, next now again we go for integral representation of this. So integral representation. So basically, unit beta transform. So basically, if you see, this is nothing a simple beta function. If you see, this is beta function, and in the beta function we introduce this function. And finally, we will give this function in the form of this one. What is this? This is your right-type function. This is your right-type function. So it means this can be also put in the form of the right-type hypergeometric function. If you take the Laplace transform of this function, so it means right-type, Whittaker transform. So Whittaker, this is your Whittaker function is this. And with combining with Whittaker function with this 2R1 series, so ultimately again we can get 4 psi 2. 4 psi 2, this right function. And next now the relationship of 2R1 with S function, I function, and right hypergeometric function. So here we can also establish the relationship with the Fox X function. Fox function also during the 1962-63. C. Fox, this was the Canadian, C. Fox, was a great mathematician. He was editor of this Canadian journal from Britain of Canadian Journal of Mathematics, and he introduced this function. And so here we can also establish this function in the form of this this is your x function. So this x function. So one can also connect this function with S function, and this the I function, and I function this I function was given by Professor V.P. Saxena in 1982, and during that period he was I think he left Surat 1980, but he submitted this paper at Surat and published after running by Gwalior. So this function was introduced by Professor B.P. Saxena, and you can also say this is the Saxena function, and this can be also established the relation into this form. This is given the relationship with your I function, and this is your right function as we earlier discussed. So it means this by putting some suitable value. So this can be also put into right function. Right function, this is P psi Q. So here we can put it P equal to 2 psi equal to this is 2 psi 1. And next now. Next some relation right there and some written relation. So earlier, so this is very computing part, that's a computational work in the section. So if you see, this is in 2001, the question that given that we earlier discussed about this one, and then he also put it in 2000, which was summarized by the version 2001 is there, and this is extension by the version 2 and a colleague in 2008. So that is given in the form of this. So this can be put in. They have to put this function to f1 tau. So this is a parameter, and ABC is other parameter. So this can be written in the form of this to f1 ABC. This can be also write like this to f1 tau z. These are the value. They are taking the value 2 numerator, contains 2 numerator and 1 denominator. So here by this, and finally we can put into so this is again, if you see this a minus b and this is c minus b minus 1. Ultimately, this is a beta type. If you see, if you forget this one for a moment, so you will get d raised to power b minus 1 into 1 minus b raised to c minus b minus 1. So this is now, so this kind of thing. So here, this is very wonderful work during this started by Jotendra 2008 and then Snehal. So this basically this conclusion made by him. So computing this a very lengthy calculation, but here this is only one line. But I think it is very difficult. Difficult to say to 8 to 10 hours for computing this degradation. I think during that period, we can sitting at mornings 8 o'clock to at evening 5 to 6 hours, 5 to 6 p.m. in the department, then again at his home, and after 1 or 2 days, he got the result. And further, it was that technique was used by Snehal in this function, and Jotendra used this technique to solve the Ajay function, and Snehal used for solving this type of hypergeometric function. So this is the recognition for this. This is your recognition now. So this is can put into this form. So here this is not F1, Z square, Z, and this is now Z is this and this is 30. But here, if you basically the beauty of this equation, you can also form some different type of differential equation if possible. But we are still thinking of this, but it's still not succeeded. So let's hope for the best possible if we get in chance in the course of time. And here, this is the integral representation of the differences and the differential formula for the right type hypergeometric function. This is in the form of the theorem 3.3.1 that is given by this 3.3.1. And here, the conditions if you see, this is a real k greater than 0, real k greater than 0, real b greater than 0. So it means all the real values that are given here, all the real values are the positive value. So, and now again, this is now 3.3.3. This is your one integral representation that is given by this. And similarly, 3.3.3.4 that is given into this form, and then 2R1 ABC tau that is this can be also put into this form. So this again one of this integer representation. And remember the condition is very same. This mode of journey lies there. That is the conversion condition. They always study for the conversion condition and there. No need to change. If suppose this any function series is the divergent meaning that's for us. So we don't touch and don't think about any divergence series. So here, this is my next one is this is theorem 3.7.7. That then this can be written into this form. That is a 3.3.12. And now here, and difference for same. So this is again the extended work of the Watsenko in 2008. So here if you put so for now this is of this function. So here, so this is some establish the relation between these two in the form of some integer representation. By integer representation of the two are one by the concept of your integration from 0 to infinity. Then 0 to infinity, then this gives in the form of this 2f1 tau tau 2. This is given in the form of this. So it means here we also consider here taking consider this that is your remote. This is this is your conversion condition, and here 3.3.4.1. This is not given. And now here, if you see 3.4.2 again, so these are the conditions I mentioned here, and this can be 2f beta is this, so this converted into this form. So this result can be independent, can be put into this form. This is called your differentiation formula. Now this knowledge, this is known as the differentiation formula. The relation between this and the right because of the function is given by this. So one formula of this. So here, so if I take this one, this can be converted into the form of the method of the function. This function basically introduced by us, I think, in 2007 when we the other part of the thesis. So this is the function. And this work and published in this the communication of the Korean Mathematics Society and integer transform in special function. This is. And next now we right-hand hypergeometric hypergeometric function of the fractional operator. So here we use the concept of this fractional calculus. So subject of the fractional calculus. But here we would like to say what is the fractional calculus? This is very interesting if you see when the concept of calculus. Why we are using calculus then again fractional calculus? The calculus means that is when we our base is for the variable or some interval that is tends to 0. And here we again use the concept of fractional. But the first order 1/2 or 1/3 or 1/4 or 1/2 or like this. So this is the order of the differences and the order of the integration. So what is the meaning of this base? What is the base? Base is suppose if we have this our variable in suppose that it means delta that tends to 0. It means so we have to check now. It means at very negligible value of the negligible value that is the delta there which is tends to 0, and that gives this that is the concept of the fractional calculus. Hello. So now this over here, we will discuss this concept of the fractional calculus. So this is concept of this. So this means here this our references are mentioned over the concept of 31, 48, 56, 60, and work of this Das, Delhi, Ilford. They were very great mathematician, wonderful mathematician. They read Menardi and Sunday, And this Tomowski, one good paper of this. This is a published in inverse of inverse of chemistry, some like this. A wonderful paper. So was the chemistry. This was the other work on our function. This methods of the function. This was methods of a function, and this also play very important role for fraction calculus in basically science, engineering, it's a fluid, and the differential and relaxation, oscillation, and so many differential equations, so many diffusion equations, chemical reactions, etc., etc., etc. So on. So basically, and the propagation of the seismic waves, dynamic process will solve the similar process on the structure. And here we take the concept of this ELSA and one flow, then Kala, Saxena, flow and one flow. And this is if you go working about working fractional calculus, this was a very wonderful book. This is the 664 and Berlubne 66. So here we get some property like this. And we also use this Prajapati and this 68 and Shukla 65 and Surat quarter in 99 again. That's like an approach is study of the intelligent operator. So here we also some extended this in some property of this function, whatever is generalized the right hand hypogeometric function. So we can use like this equations. So they were on the work this total based on the fractional calculus. So this is the 4.1.1 and 4.1.2, and here. Let's come on. So V1 liable fractional derivative. This is defined by this, and giving the formula like this. This is 4.1.3. This is the formula, and this is called left hand left with the left side of the fractional difference in fractional integral of the order, and here this is called right. This is left, and this is the right. And this is given the concept of 4. So representation of this 4.1, 4.1.5, and 4.1.6. And referring to do generalized Bessel polynomial. This work I think 1953, I think most probably 1953, 54, something like this. And that giving 2L0 form. So ultimately, this is the Bessel polynomial minus n, alpha plus n minus 1 minus this. Ultimately, here, your numerator is a 0, the numerator is a 0, and there are two parameters. There are two parameters in, numerator are 2, numerator are 2 and the denominator are without any parameter. So this is a 4.1.10, 4.1.10. So here we can see the concept of the Srivastava and Manochar books. So this is the function analytic, and this is your disk, and power series expansion function app that can be written into this form, and this is taking some your negation, this derivation of this. So ultimately this minus is plus ultimately. So here we can put into this form, given into this form of this work, and here fractional operator and the generalized hypergeometric function. This, so consider function FT. So FT is defined by this. FT defined by this. So this is we can say this is A going to K, B going to K. If I put out B, this is now the gamma B plus A here. So it means gamma B here. Ultimately B going to K. And here K is there. So this factorial K is coming. So here factorial K is coming. We can also write 1 going to K into the factorial K. 1 going to K means that is the factorial K. So this can be put into this form. And now here we have some properties. So there are some properties in the form of this 4.2.1, 4.2.1, and 4.2.2, 4.2.3, 4.2.4, and this is 4.3.1. This is the property of the function. So here we define like this. So operating this I lambda. This is I is it, so this is I lambda is RT, C, V, AB, so this is RT, the C lambda plus B and AB is the 4.3.1, and this is the 4.3.2, and here that is your Laplace transform of this. So that is for that can put it into this form. So finally, this is given into this form. So Yn. What is Yn? Yn. This is your Bessel polynomial. It means this is very interesting. So this can be converted into the Bessel polynomial into by using the condition by taking the Laplace transform. By taking the Laplace transform, is converted into form of the Bessel polynomial. Next, now here again, here this 4.3.4 and 4.3.5, and here imposing the conditions n small n belongs to this n and alpha n constant, the Laplace transform of this again this becomes also a generalized Bessel polynomial, in the form of the 4.3.3.6. And fractional, integral, and differential operator related to the function is 2f1. 2f1. So 2f1 is this. 2f1, so alpha belongs to R plus, and all A, B, C, mu, omega belongs to C, and real value is greater than 0. Then we will get this is also ultimately for this omega belongs to C, and this. So finally, on first one is and give it into this form. This is 4.4.1, and the second one is this is 4.4.2. This is 4.2.2. Ultimately, this if you see 2R1 is this. So it will be by using this condition. So ultimately, you see the C is the C replaced by C minus B. C minus B, and omega becomes omega. There is no change in omega. Omega gives us x minus a. So x minus a is this. Power is tau is here. There is no change in this, only except this C. Ultimately, this will partially affect on parameter. Parameter means this is your this parameter. This is your C. The C. Next property now here. If mu lies between 0 and 1, and this is mu, and mu lies between 0 and 1. This is an open interval, and this is your closed interval. So it means finally, then imposing all the conditions. So finally, we can say this becomes into this form. This is 4.4.3. This form. And that's a corollary. This is if we put some specific value, so that also put into form into this form 2R1. This is 2R1. Lambda is this access to power mu divided by gamma mu plus 1. And here one is one can see now here very interesting. This is A is this, A is this, 1 is this, 1 is this. Here 1 is here, so 1 is replaced by mu plus 1. Tau is this, lambda is this, lambda is x is this, power is tau. This is now tau is this here, so ultimately here you will get. So finally, if you see there is change in this now. So it means mu is replaced by, 1 is replaced by 1 plus mu in this case. And condition is this is a product of the lambda x to the power tau. So this must be, if I take this is just like this, it means this, it means that is convergent. This convergent means which must be the less than 1. And we can also go for find some value when this is equal to 1. When it is equal to 1, then we can use the concept of some integral representation and the beta gamma function. So again, we can also input some specific condition and get the result. If we're taking this is this is equal to 1. And now here some special cases are given. So I'm skipping this, and this is if you interested, then it's a 4.4.5, 4.4.6. Now right type generalized hypergeometric function. The right type hypergeometric function. The first now it is 2R1 is this. 2R1 is this. So this can be put into this form. If you see here, gamma is this, gamma is this, and this is your going to n is this. Okay. So basically, if it's a right in the case of the right contain all your parameter must be the form of the gamma function. So here, all parameters are not in the gamma function. Here, simple the one, this one, and this one. So this one is this, and c plus k going divided by n going to n is the title. This is your gamma function. This is your gamma function. Clear? And this is your a going to n. A going to n is this, and c plus k divided by n. This is going to n is this. Z raised to power n divided by factorial n and m raised to power n. Given. Putting n equal to 1, it reduces it to f1. To f1. Some property of this function. So here again, use this operator. So this is now so our condition, the 4.1. If you see theorem 4.5.1, this is your theorem, and these are the condition. If you impose over this, so this can be written as a 4.5.1. Similarly here by this, then bounded. This must be the bounded on alpha beta. That is your for the level, and here by imposing the condition of this one. Here, this is 4.5.2, and we have this condition 2. So basically, what the need is this. Basically, if you say want to know, that must be we have to put this must be exist as well as convergent as well as the bounded. If I use like this, so ultimately, if you see finally you will get this must be the bounded. So this will be bounded. So here we impose the condition for the boundedness. So we look for the B and for the that is represented by in the form of the 4.5.3. And next in the 4.5 sorry 4.5. Next now we take the theorem. This theorem. So this can be also put in the form of the summable function. This f belongs to L alpha beta. This is your 4.5.4. And this is I published part of this theorem this in the Korean Journal of Mathematical Society. And this is for 4.4.1, 4.4.2. This is all 4.5.1 to 5.3. Section has been published in the following journal. That is your advancing in the differentiation. Now, sequence of the function is associated with the right type generalized hypergeometric function. So here, this is little bit using some technique of this. You can say this operation technique. This is in Srivastava Singhal, I think 1978, and here was 78, 71, sorry, 71. This is given. Mira? Hello?
Yes, sir.
इस सिंगल सर को जानती हो?
हाँ जी सर.
हाँ, सिंगल
दवे सर के गाइड है सर.
आप सर तुम्हारे गुरु के
जेपी
गुरु?
सिंगल सर.
हाँ, सिंगल
Yes,
सर.
sir.
जी
सर.
So the single Srivastava single that is defined. This is by using some operational technique. This is the 5.1, 1.1. So this is now an action. And A. Srivastava extended this into this form. So basically, if you see changes here, exponential of p x to power r. Okay, and here you use the, and this is now x to power k plus 1, and this is d. D is your operator, and whole raised to power n. So he extended this x to power x plus xd. Clear? So ultimately this operator has been extended by this. Extended by, if you see now here x to power alpha, x to power alpha, no problem, no change. And here p is this exponential of this, so your pkx. Can define pkx. Pk is the polynomial. So basically here they consider anything, this some, so p is some numerical value. And here we take pk is the polynomial. Ultimately pk is new, so it was pk 2x, 3x, 4x, what I like it. But here, if you see minus pkx, the pkx means pk is a polynomial of order k. It means polynomial. So we use the exponential series polynomial. Exponential series in the form of the exponential series containing this variables are in the form of polynomial. This is polynomial. Okay. And here in the sequence, we use term now. So it means in the sequence, we use the concept of the right type hypergeometric function in this work and define into this form. And if you say 2R1 is this, pkx is this. It means your argument, our argument was z when in our earlier slides, if you see z is replaced by pkx. It means that becomes your that is in the form of the polynomial. And this is your operator. Here take this is alpha t, this is your operator form, and this is x is to power delta, and 2R1 is series is this, and all this now pk defined, x is defined in the open interval 0 to infinity. Open interval 0 to infinity, it means here we consider the function to be bounded, but greater than 0, less than, obviously this is the less than infinity. And here this can be put in the form of like this, so in 5.1.4. So this is defined. So ultimately, if you see what is this? This is your parameter. This is operator. So we extended the operator like this. So x is to power n alpha, x is x. This is s plus xb, s plus alpha plus xb, s plus 2 alpha plus xb, up to so on. This x plus n minus 1 alpha plus xb with d given by d over dx. This is well known. And 1975, the Srivastava and the Levi proved the following results. So he given same this result by using this operation techniques. That is given by this, and all this that you define into this form. This is now, and here this is again polynomial and degree n by q in y. We define into this form. Defined by this one. V, this is gamma, with qk and n minus qk, delta vk, and v minus to power k. So here genetic relation. So first we have to find out the genetic relation. So genetic relation means, so basically genetic relation means it is that when we are having polynomial, it means when polynomial is there, it means this is most important for finding, in the case of polynomial, finding the finite summation formula. If finite summation formula for any polynomial is not applicable or not receive any formula such type or not able to drive formula, it means we have to complete some mistake to decide whether it is polynomial or not polynomial. Clear? So it means this is most important property of this. So this is the given into this form, and this can be written into this form. Finally, if you see x, this alpha, and this now, and function, relative function of the function. This is a function, and this function already this is functions, and this is defined into this form to 5.1.3. Okay. So finally we will get 5.2.1, and this is the second one is 5.2.2, and this is your from this book 5.2.3. This is your negative function for this. Yes, similarly now here n is equal to 0 to infinity. This can be written in the form of 5.2.4, and e, this can be represented in the form of 5.2.4, and this is your and 0 to infinity, and this can be represented into form of this one 5.2.3. And the finite summation formula for the function uh, for this function. So here again we can operate two finite summation formula. So that is given into this form 5.3.1 and 5.3.2, and bilateral generating relation. Bilateral generating relation. So it will 5.1 by 11 and 5.2, and so this observe this given into this form, and finally this is your operator is this. So this can be written into this form. So finally this delta x and psi given like this. So basically here simple we are going to put all the corresponding values, and we as a bilateral generating relation for this. This can also be obtained 5.4.1 in the form of this. And here, when we got some of this type of function, we in this paper, Ibrahim generated implemented the map bill, and basically this is different type of polynomials, different type of the graph. Very interesting graph if you see, and this is your coding, and the graph is this okay. The 5.1, 5.13, the 5.13 that is defined, given into this graph. So here we put some different values of this 155 and this 111 x 244. So it will be different types of this. If you see, that is the graph of the polynomial. This is. And now here, this is your 3D plot of this function. This is your 3-dimensional plot, and this is your 2-dimensional. So here, if you put the corresponding values, according 1 orange line, 2 is the green line, 3 is the red line. So different 3 is the red line, 3 is the red, 4 is blue line. Blue line is this. So ultimately, if I put yeah, b is equal to 4. B is equal to 4, so you will get this type graph. And if I say this is 2, so you will get this is your green line. This is green line. So now you get green line, blue line, and red line, and this is your complex 3D formula. So we convert this into the 3 dimensions, and this was your 2 dimensions. And the graph of this again by putting some corresponding values. These are the values. So this again we will get, but this graph all the graph plotted in by using the Maple software. And this work was published in Journal of Mathematical Science and Research Journal. And these are the references. This is very good book. Those who are interested about on this field. This and this paper, this is 1990 now. So I was in impression that 1953. So I was in impression. It's 1919, very old paper. But this is old, a very basic paper, very interesting paper. This one is this one, and one can really can learn the techniques basically for the orthogonal polynomial. This is your Bessel polynomial. And this book. These two books are ready for this book. This special from their application. Very interesting. This is from Here you will get so many applications of the special function. Asymptotic and zero, this is no asymptotic of zero of the right function. And and this is this Mathai books. This is a very good book. And this these three were the 56, 57, 58. And this is a basic book for the generative function. Those who are interested in work on generative function, they can use this one right book. And this is basically the book of Miller, K.S. Miller, and the Biroff. Biroff's book. And this one. And here I would like to suggest you this book. Those who are interested in the fractional calculus. This is small paper. This is the work, the contribution made by the Ibrahim, the plot and the graph and all the sectors of the function. And by using the operational technique, this, over the last one, this last article, thank you so much. Last slide is missing. Thank you so much for bearing me. And so,
Thank you, sir.
if you had any discussion.
Thank you very much, sir. Now, with your kind permission, sir, may I take some of the questions from the participants?
Yeah, most welcome.
So, sir, first question from the participant is, what is the significance of studying the R function?
R function basically that is the extension of this. One thing in the mathematics is the curiosity, if you know. Generally, हम लोग क्या करते हैं coordinate जब come 1 dimension, 2 dimension, 3 dimension, but in the mathematics it goes up to n dimension, whether it is existing or not existing. Significance is just like only in mathematics. If you go any conference and anywhere, generally people used to ask you, what is the use of this function? So basically, I can remember here. This is we initiated this. We started. Whatever the significance comes, it is for the time to say.
Yes.
This is not in my hand right now to say this. Basically, suppose a person who is working in mechanical engineering, if you feel that this may be very much useful, they may be useful, then ultimately they will consider this function image 1. So then you can say, well, this is an application of this field in your mechanical engineering. But here we started to work on this. By the way, that come in our mind, so I started to work. That is simple extension of this your hypergeometric function.
Yes, sir. The second question is, do we have a differential equation or a fractional differential equation satisfied by generalized function to R1?
As yet, not.
Okay.
As yet, not. We also tried, but unfortunately, we are not. We failed to get it.
Okay, sir. And the last one is, can we associate a probability distribution function with generalized function?
This probability we can use it. Basically, this function can be used in your statistics. We can use it in the statistics.
Yes. Thank you very much, sir, for this session of question answering. Sir, on behalf of the Charoset family, I am very much thankful to you for enlightening us through this talk about right type generalized hypergeometric function to R1 and its properties. You have shown its relation with Fox H function, I function, right function, and also discussed about the properties like Malin-Barnes contour integral, Laplace transform, generating function relations. Also, you have discussed about the role of this function as a fractional operator. So I think that this is a very informative session and it will be helpful to all researcher and faculties who have joined. So on behalf of entire Charuset family, I'm really thankful to you as you have accepted our invitation and spent your valuable time and knowledge with all of us. Sir, actually, in this virtual mode, since corona pandemic situation we have, so I am representing a token of gratitude from Charuset family and presented e-memento to you, sir. Please accept it virtually.
Okay, thank you. Thank you so much.
Yeah, thank you very much, sir, once again.
Okay, thank you. Thank you.
Can I
बोले जोशी जी कैसे हैं?
नमस्कार
Welcome, sir.
First, congratulations to the organizer who is doing the wonderful job.
Thank you.
And Shukla sahab, I need your help. Geometric function theory pe, if you have some special book, if you can recommend to us, because present geometric function theorems.
मैं उस पर ज़्यादा नहीं किया मेरे को सीजन देखना पड़ेगा मुझे.
Because I now studied a few of the papers from the geometric function series and theorems, so that's I thought कि मैं आपसे कुछ राय ले लूँ इससे.
वैसे उसका तुम चाहो अगर आप चाहो तो कॉमिटोरिक्स में थोड़ा बहुत यूज कर सकते हो उसका मैन्युप्रेटिक्स.
Okay.
कॉमिटोरिक्स वगैरह वाले.
Okay.
क्योंकि बेसिकली वही लगा के that's nowadays if you think very interested, generally people want to know some work that is I would like to that is in the form of some applicable mathematics. So applicable mathematics means what we do. So it means basically this is time of the marketing. And everybody is expecting for the mathematician to do something for them.
Okay.
Something. Basically, if you're working in any engineering college, a person working in some computer science, he will expect, okay, you are a mathematician, you must know about this. If you are some chemical engineer, okay, you must this one mathematics. If you are some this mechanical, electronic, civil, okay, you are mathematician, you must know the mechanical, civil, electrical. So people are expecting you. It means that you are just like a god. तो वो जो चीज आजकल चल रहा है ना वो सबसे इम्पोर्टेंट है कि आपको थोड़ा बहुत नॉलेज आपको हर एक फील्ड का आपको करना पड़ेगा. थोड़ा बहुत बोलेंगे सर्वाइव करने. और इसमें जैसे कभी मेरा वो जो किसी ने लास्ट वाले ने पूछा वो जो इसमें जैसे हाइपोजोमेट्रिक फंक्शन में तो इसलिए बोलूँ क्योंकि जो नए लोग हैं जो नए हाइपोजोमेट्रिक फंक्शन से वो लोग फैमिलियर भी है तो हाइपोजोमेट्रिक फंक्शन को थोड़ा काम करें और उस काम में बेसिकली इसमें स्कोप बहुत उसमें है कि आप स्टैटिक्स में भी आप यूज कर सकते हो. तो ये स्टडीज में अगर थोड़ा बहुत भी आप उसका कॉम्बिनेशन जैसे राइट टाइप के साथ बना कर लो मिटेज डेफर फंक्शन के साथ कॉम्बिनेशन करें अल्टीमेटली देन वी कैन गेट so many good results and that may be also very much useful in the field of statistics.
Thank you, sir. It's very nice to see you virtually. Thank you so much.
Okay, thank you Meera.
Yeah, thank you, sir. Actually, sir, we have Dave sir is also present over here.
अच्छा. अभी एक्चुअली वो चाइना में भी वो है वहाँ पे वो क्या नाम मारवाड़ी में तो एक मीटिंग है.
जी सर, no problem sir. Okay sir, thank you very much once again.
Okay, thank you all of you. Have a good day.
Same to you. Dear participants, feedback link is already shared. I request all of you to fill up this link as soon as possible and have a nice day. We will meet tomorrow session. Tomorrow's session will be commence at 10 o'clock. So please join this link of day 2, session 1, sharp at 9:45. Have a great day. Take care.
Thank you, ma'am.